This video is about the exponent rules, rules that govern expressions like 2 to the 5th or x to the n. 2 to the 5th is just shorthand for 2 times 2 times 2 times 2 times 2, written 5 times. And similarly, x to the n is just x multiplied by itself n times. When we write these expressions, the number on the bottom that's being multiplied by itself is called the base. And the number at the top, telling us how many times we're multiplying the base by itself, is called the exponent. Sometimes the exponent is also called the power. The product rule says that if I have x to the power of n times x to the power of m, that's the same thing as x to the n plus m power. In other words, when I multiply two expressions with the same base, then I can add their exponents. For example, if I have 2 cubed times 2 to the 4th, that's equal to 2 to the 7th. And that makes sense because 2 cubed times 2 to the 4th means I multiply 2 by itself 3 times, and then I multiply that by 2 multiplied by itself 4 times, and in the end I have 2 multiplied by itself 7 times, which is 2 to the 7th. I'm just adding up the number of times it's multiplied in each piece to get the number of times it's multiplied total. The quotient rule says that if I have x to the n power divided by x to the m power, that's equal to x to the n minus m power. In other words, if I divide two expressions with the same base, then I can subtract their exponents. For example, 3 to the 6th divided by 3 squared is going to be 3 to the 6 minus 2, or 3 to the 4th. And this makes sense because 3 to the 6th means I multiply 3 by itself 6 times, and then I divide that by 3 multiplied by itself twice. So when I cancel out 3's, I have 4 3's left. Notice that I have to subtract the number of 3's on the bottom from the number of 3's at the top. To get my number of 3's remaining. That's why I subtract my exponents. The power rule tells us if I have x to the n power raised to the m power, that's the same thing as x to the n times m power. In other words, when I raise a power to a power, I get to multiply the exponents. For example, 5 to the 4th cubed is equal to 5 to the 4 times 3, or 5 to the 12th. And this makes sense because 5 to the 4th cubed can be thought of as 5 to the 4th times 5 to the 4th times 5 to the 4th. Expanding this out some more, that's 5 times 5 times 5 times 5 times the same thing times the same thing again. So I have 3 groups of 4 fives, which is a total of 3 times 4, or 12 fives. The next rule involves what happens when I raise a number or a variable to the 0th power. It turns out that anything to the 0th power is equal to 1. Usually this is just taken as a definition, but here's why it makes sense to me. If you have something like 2 cubed divided by 2 cubed, well, certainly that has to equal 1. Anything divided by itself is just 1. But using the quotient rule, we know that this is the same thing as 2 to the 3 minus 3, because when we divide two things with the same base, we get to subtract their exponents. Therefore, this is the same thing as 2 to the 0. So 2 to the 0 has to equal 1. In order to make it work with the quotient rule. And the same argument shows that anything to the 0 power has to be equal to 1. What happens when we take something to a negative power? X to the n is equal to 1 over x to the n. Again, most people just take this as a definition of a negative exponent, but here's why it makes sense. If I take something like 5 to the 7th times 5 to the negative 7th, then by the product rule, this has to equal 5 to the 7 plus negative 7, which is 5 to the 0, and we just said that that is equal to 1. Now I have the equation 5 to the 7th times 5 to the negative 7th equals 1. If I divide both sides by 5 to the 7th, I get that 5 to the negative 7th has to equal 1 over 5 to the 7th. So that's where this rule about negative exponents comes from. It has to be true in order to be consistent with the product rule. Finally, let's look at fractional exponents. What does an expression like x to the 1 over n really mean? Well, it means the nth root of x. For example, 64 to the 1/3 power means the cube root of 64, which happens to be 4. And 9 to the 1/2 means the square root of 9, which is usually written without that little superscript up there. Now the square root of 9 is just 3. Fractional exponents also make sense. For example, if I have 5 to the 1/3 and I cube that, then by the power rule, that's equal to 5 to the 1/3 times 3, which is just 5 to the 1, or 5. So in other words, 5 to the 1/3 is the number that when you cube it, you get 5. And that's exactly what's meant by the cube root of 5. The cube root of 5 is also a number that when you cube it, you get 5. The next rule tells us we can distribute an exponent over a product. In other words, if we have a product, x times y, all raised to the nth power, that's equal to x to the n times y to the n. For example, 5 times 7, all raised to the third power, is equal to 5 cubed times 7 cubed. And this makes sense, because 5 times 7, all raised to the cube power, can be expanded as 5 times 7 times 5 times 7 times 5 times 7. But if I rearrange the order of multiplication, this is the same thing as 5 times 5 times 5 times 7 times 7 times 7, or 5 cubed times 7 cubed. Similarly, we could distribute an exponent over a quotient. If we have the quotient x over similar times 7 times 7 times 7, or 5 cubed times 7 cubed. Similarly, we could distribute an exponent over a quotient. If we have the quotient x over y, all raised to the n power, that's the same as x to the n over y to the n. For example, 2 sevenths raised to the fifth power is the same thing as 2 to the fifth over 7 to the fifth. This makes sense because 2 sevenths to the fifth can be expanded as 2 sevenths multiplied by itself 5 times, which can be rewritten as 2 multiplied by itself 5 times divided by 7 multiplied by itself 5 times. And that's 2 to the fifth over 7 to the fifth as wanted. We've seen that we can distribute an exponent over multiplication and division. But be careful, because we cannot distribute an exponent over addition or subtraction. For example, a plus b to the n is not generally equal to a to the n plus b to the n. A minus b to the n is not generally equal to a to the n minus b to the n. And if you're not sure, just try an example with numbers. For example, 2 plus 3 squared is not the same thing as 2 squared plus 3 squared. And 2 minus 3 squared is definitely not equal to 2 squared minus 3 squared. In this video, I gave 8 exponent rules, which I'll list again here. There's the product rule, the quotient rule, the power rule, the zero exponent, the negative exponent, the fractional exponent, and they're the 2 rules involving distributing exponents across multiplication and division. In another video, I'll use these exponent rules to rewrite and simplify expressions involving exponents. In this video, I'll work out some examples of simplifying expressions using exponent rules. I'll start by reviewing the exponent rules. The product rule says that when you multiply 2 expressions with the same base, you add the exponents. The quotient rule says that when you divide 2 expressions with the same base, you subtract the exponents. The power rule says that when you take a power to a power, you multiply the exponents. The power of 0 rule says that anything to the 0 power is 1 as long as the base is not 0. Since 0 to the 0 is undefined, it doesn't make sense. Negative exponents. To evaluate x to the minus n, we take the reciprocal 1 over x to the n. To evaluate a fractional exponent, like x to the 1 over n, we take the nth root of x. We can distribute an exponent over a product. A times b to the n is equal to a to the n times b to the n. And we can distribute an exponent over a quotient. A over b to the n is a to the n over b to the n. In the rest of this video, we'll use these exponent rules to simplify expressions. For our first example, we want to simplify 3 times x to the minus 2 divided by x to the 4th. There's several possible ways to proceed. As the product
What we're going to do in this video is talk about factors and factor pairs. Now, when we talk about factors, these are really numbers that can be multiplied together to make some number. So, for example, if I were to talk about factors of 6, I could multiply 2 times 3 to get 6. And so we would say that 2 and 3 are factors of 6. In fact, we would also say that 2 and 3 is a factor pair for 6, because when I multiply those two, I can get 6. Now, to think about all of the different factor pairs for a number, we could think about it in terms of area. How can we make a rectangle with area 6? Well, you could do it if it's 2 units by 3 units, so it could look something like this. I'll just hand draw it. So let's say let's say our rectangle looks like this. So it has 2 rows and then 3 columns, and let's say these all have equal area. It's hand-drawn, but you can see that the area here would be 2 times 3, which would be equal to 6 square units. Now, what are other ways to get to an area of 6? Well, you could have something that is 1 row, but then it has 6 columns. So maybe it looks something like this. It looks like this. So it's 1 row, and then you have 1, 2, 3, 4, 5, and I want them all to be roughly the same size. So it's 1 times 6 would be also an area of 6. So that would be another factor pair. We know that 2 times 3 is equal to 6, and we know that 1 times 6 is equal to 6. And these are actually the 2 factor pairs for 6. And we can do it with larger numbers. We could think about, what about all the factor pairs for something like 16? Pause this video. In this video, I want to talk a little bit about what it means to be a prime number. And what you'll see in this video, or what you'll hopefully see in this video, is it's a pretty straightforward concept. But as you progress through your mathematical careers, you'll see that there's actually fairly sophisticated concepts that can be built on top of the idea of a prime number. And that includes the idea of cryptography, and maybe some of the encryption that your computer uses right now could be based on prime numbers. If you don't know what encryption means, don't have to worry about it right now. Just need to know that prime numbers are pretty important. So I'll give you a definition. And the definition might be a little confusing, but when we see it with examples, it should hopefully be pretty straightforward. So a number is prime if it is a natural number, and a natural number, once again, just as an example, these are like the numbers 1, 2, 3. So essentially the counting numbers starting at 1, or you could say the positive integers. It is a natural number divisible by exactly two numbers, or two other natural numbers. Actually, I shouldn't say two other. I should say two natural numbers. So it's not two other natural numbers, divisible by exactly two natural numbers. One of those numbers is itself, and the other one is 1. Those are the two numbers that it is divisible by. And that's why I didn't want to say exactly two other natural numbers, because one of the numbers is itself. And if this doesn't make sense for you, let's just do some examples here and figure out if numbers are prime or not. So let's start with the smallest natural number, the number 1. So you might say, look, 1 is divisible by 1, and it is divisible by itself. You might say, hey, 1 is a prime number. But remember, part of our definition, it needs to be divisible by exactly 2 natural numbers. 1 is divisible by only 1 natural number, only by 1. So 1, although it might be a little counterintuitive, is not 1 is not prime. Let's move on to 2. Let's move on to 2. So 2 is divisible by 1 and by 2, and not by any other natural numbers. So it seems to meet our constraint. It has 2, it's divisible by exactly 2 natural numbers. Itself, that's 2 right there, and 1. So 2 is prime. So 2 is prime. And I'll circle the prime numbers. I'll circle them. Well, actually, let me do it in a different color since I already used that color for the. Well, I'll just circle them. I'll circle the numbers that are prime. Now let's 3. And 2 is interesting because it is the only even number that is prime. If you think about it, any other even number is also going to be divisible by 2, above and beyond 1 and itself. So it won't be prime. We'll think about that more in future videos. Let's try out 3. Well, 3 is definitely divisible by 1 and 3, and it's really not divisible by anything in between. It's not divisible by 2. So 3 is also a prime number. Let's try 4, and I'll switch to another color here. Let's try 4. Well, 4 is definitely divisible by 1 and 4, but it's also divisible by 2. 2 times 2 is 4. It's also divisible by 2. So it actually has, it's divisible by 3 natural numbers, 1, 2, and 4. So it does not meet our constraint for being prime. Let's try out 5. So 5 is definitely divisible by 1. It's not divisible by 2. It's not divisible by 3. It's not divisible by 4. Exactly divisible by 4. You could divide them into it, but you would get a remainder. But it is exactly divisible by 5, obviously. So once again, it's divisible by exactly 2 natural numbers, 1 and 5. So once again, 5 is prime. Let's keep going just so that we see if there's any kind of a pattern here. And then maybe I'll try a really hard one that tends to trip people up. So let's try the number 6. It is divisible by 1. It is divisible by 2. It is divisible by 3, not 4 or 5, but it is divisible by 6. So it has 4 natural number factors, I guess you could say it that way. And so it does not have exactly 2 numbers that it is divisible by. It has 4, so it is not prime. Let's move on to 7. 7 is divisible by 1, not 2, not 3, not 4, not 5, not 6, but it's also divisible by 7. So 7 is prime. I think you get the general idea here. How many natural numbers like 1, 2, 3, 4, 5, the numbers that you learned when you were 2 years old, not including 0, not including negative numbers, not including fractions and irrational numbers and decimals and all of the rest, just regular counting positive numbers. If you have only 2 of them, if you're only divisible by yourself and 1, then you are prime. And the way I think about it, if we don't think about the special case of 1, prime numbers are kind of these building blocks of numbers, is that you can't break them down anymore. They're almost like the atoms. If you think about what an atom is, or what people thought atoms were when they thought it was kind of the thing that you couldn't divide anymore. We now know that you could divide atoms, and actually if you do, you might create a nuclear explosion. But it's the same idea behind prime numbers. In theory, in prime numbers, it's not theory. We know you can't break them down into products of smaller natural numbers. Things like 6, you could say, hey, 6 is 2 times 3. You can break it down. And notice, we can break it down as a product of prime numbers. We've kind of broken it down into its parts. 7, you can't break it down anymore. All you can say is that 7 is equal to 1 times 7. And in that case, you really haven't broken it down much. You just have the 7 there again. 6, you can actually break it down. 4, you can actually break it down as 2 times 2. Now, with that out of the way, let's think about some larger numbers and think about whether those larger numbers are prime. So let's try 16. So clearly, any number is divisible by 1 and itself. So any natural number you put up here is going to be divisible by 1 and 16. So you're always going to start with 2. So if you can find anything else that goes into this, then you know you're not prime. And 16, you could have 2 times 8. You can have 4 times 4. So it's got a ton of factors here, above and beyond just the 1 and 16. So 16 is not prime. What about 17? 1 and 17 will definitely go into 17. 2 doesn't go into 17. 3 doesn't go. 4, 5, 6, 7, 8, 9, 10, 11. None of those numbers. Nothing between 1 and 17 goes into 17. So 17 is prime. And now I'll give you a hard one. This one can trick a lot of people. What about 51? Is 51 prime? Is 51 prime? And if you're interested, maybe you could pause the video here and try to figure out for yourself if 51 is a prime number. If you can find anything other than 1 or 51 that is divisible into 51. It seems like, wow, this is kind of a strange number. You might be tempted to think it's prime, but I'm now going to give you the answer. It is not prime because it is also divisible by 3 and 17. 3 times 17 is 51. So hopefully that gives you a good idea of what prime numbers are all about, and hopefully we can give you some practice on that in future videos or maybe some of our exercises. Determine whether the following numbers are prime, composite, or neither. So just as a bit of review, a prime number is a natural number, so one of the counting numbers, 1, 2, 3, 4, 5, 6, so on and so forth, that has exactly two factors. So its factors are 1 and itself. 1 and itself. So an example of a prime factor is 3. There's only two natural numbers that are divisible into 3. 1 and 3. Or another way to think about it is the only way to get 3 is a product of other natural numbers is 1 times 3. So it only has 1 and itself. A composite number is a natural number that has more than just 1 and itself as factors. And we'll see examples of that. And neither, we'll see an interesting case of that in this problem. So first, let's think about 24. So let's think about all of the, I guess you could think of it as the natural numbers or the whole numbers, although 0 is also included in whole numbers. Let's think of all of the natural counting numbers that we can actually divide into 24 without having any remainder. We'd consider those the factors. Well, clearly it is divisible by 1 and 24. In fact, 1 times 24 is equal to 24. But it's also divisible by 2. It's also divisible by 2. 2 times 12 is 24, so it's also divisible by 12. And it is also divisible by 3. 3 times 8 is also equal to 24. And even at this point, we don't actually have to find all of the factors to realize that it's not prime. It clearly has more factors than just 1 and itself. So then it is clearly going to be composite. Composite. This is going to be composite. Now, let's just finish factoring it just since we started it. It's also divisible by 4, and 4 times 6 had just enough space to do that. 4 times 6 is also 24. So these are all of the factors of 24, clearly more than just 1 and 24. Now let's think about 2. Well, the non-zero whole numbers that are divisible into 2, well, 1 times 2 definitely works, 1 and 2. But there really aren't any others that are divisible into 2. And so it only has two factors, 1 and itself. And that's the definition of a prime number. So 2 is prime. 2 is prime. And 2 is interesting because it is the only even prime number. Only even prime number. And that might be common sense to you because by definition, an even number is divisible by 2. An even number is divisible by 2. So 2 is clearly divisible by 2. That's what makes it even. But it's only divisible by 2 and 1. So that's what makes it prime. But anything else that's divisible, that's even, is going to be divisible by 1 itself, and 2. Any other number that is even is going to be divisible by 1 itself and 2. So by definition, it's going to have 1 in itself and something else. So it's going to be composite. So 2 is prime. Every other even number other than 2 is composite. Now here's an interesting case. 1. 1 is only divisible by 1. So it is not prime technically because it only has 1. It only has 1 as a factor. It does not have two factors. 1 is itself, but in order to be prime, you have to have exactly two factors. 1 has only one factor. In order to be composite, you have to have more than two factors. You have to have 1, yourself, and some other things. So it's not composite. So 1 is neither prime nor composite. 1 is neither. And then finally, we get to 17. 17 is divisible. 17 is divisible by 1 and 17. It's not divisible by 2, not divisible by 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, or 16. So It is. It has exactly two factors, 1 and itself. So 17 is, once again, 17 is prime. Write the prime factorization of 75. Write your answer using exponential notation. So we have a couple of interesting things here. Prime factorization, and they say exponential notation. We'll worry about the exponential notation later. So the first thing we have to worry about is what is even a prime number. And just as a refresher, a prime number is a number that's only divisible by itself and 1. So examples of prime numbers. Let me write some numbers down. Prime, not prime, not prime. So 2 is a prime number. It's only divisible by 1 and 2. 3 is another prime number. Now 4 is not prime. 4 is not prime because this is divisible by 1, 2, and 4. We could keep going. 5, well 5 is only divisible by 1 and 5. So 5 is prime. 6 is not prime because it's divisible by 2 and 3. I think you get the general idea. You move to 7. 7 is prime. It's only divisible by 1 and 7. 8 is not prime. 9, you might be tempted to say is prime, but remember, it's also divisible by 3. So 9 is not prime. Prime is not the same thing as odd numbers. Now if you move to 10, 10 is also not prime, divisible by 2 and 5. 11, it's only divisible by 1 and 11. So 11 is then a prime number. And we could keep going on like this. People have written computer programs looking for the highest prime and all of that. So now that we know what a prime is, a prime factorization is breaking up a number like 75 into a product of prime numbers. So let's try to do that. So we're going to start with 75, and I'm going to do it using what we call a factorization tree. So we first try to find just the smallest prime number that will go into 75. Now the smallest prime number, 2. Does 2 go into 75? 5. Well, 75 is an odd number, or the number in the ones place, this 5 is an odd number. 5 is not divisible by 2, so 2 will not go into 75. So then we could try 3. Does 3 go into 75? Well, 7 plus 5 is 12. 12 is divisible by 3, so 3 will go into it. So 75 is 3 times something else. And if you've ever dealt with change, you know, if you have 3 quarters, you have 75 cents. Or if you have 3 times 25, you have 75. So this is 3 times 25. And you could multiply this out if you don't believe me. Multiply out 3 times 25. Now, is 25 divisible by, you can give up on 2. If 75 wasn't divisible by 2, 25 is not going to be divisible by 2 either. But maybe 25 is divisible by 3 again. So if you take the digits 2 plus 5, you get 7. 7 is not divisible by 3, so 25 will not be divisible by 3. So we keep moving up. 5. Is 25 divisible by 5? Well, sure. It's 5 times 5. So 25 is 5 times 5. And we're done with our prime factorization because now we have all prime numbers here. So we can write that 75 is 3 times 5 times 5. So 75 is equal to 3 times 5 times 5. We can say it's 3 times 25. 25 is 5 times 5. 3 times 25. 25 is 5 times 5. So this is a prime factorization, but they want us to write our answer using exponential notation. So that just means if we have repeated primes, we can write those as an exponent. So what is 5 times 5? 5 times 5 is 5 multiplied by itself 2 times. This is the same thing as 5 to the second power. So if we want to write our answer using exponential notation, we could say this is equal to 3 times 5 to the second power, which is the same thing as 5 times 5. We're asked, what is the prime factorization of 36? Let me get my little scratch paper out. So the prime factorization of 36. So let's start with the smallest prime number we know, and that is 2. And think about, does 2 go into 36? Well, sure it does. 36 is 2 times 18. So we can write that down. 36 is 2 times 18. So now we have 36 as a product of a prime number, and 18 is clearly a composite number. It has factors other than 1 and 18. So let's try to factor this further. So is this divisible by 2? Sure. 18 is 2 times 9. 2 times 9. So now 9 is a composite number that we haven't fully factored. Obviously, the 2's are both prime. 9 is not divisible by 2, but it is divisible by 3. 9 is 3 times 3. So we can say that 36 is equal to 2 times 2 times 3 times 3. This is its prime factorization. All of these numbers are prime. So now let's input that. Let's input that into to make sure we got it right. 2 times 2 times 3 times 3. And you can check yourself. If you have the product of numbers that are all prime, and the product actually is 36, you have successfully prime factorized a number. Let's do a couple more of these. What is the prime factorization of 30? So I'll get my scratch paper out again. So we'll do the same process. So 30, well, it's divisible by 2, so we can write that as 2 times 15. 15 isn't divisible by 2, but it is divisible by 3. It's the same thing as 3 times 5. And both 3 and 5 are prime numbers. They are only divisible by 1 and themselves. So the prime factorization of 30 is 2 times 3 times 5. Let's enter that in. So it is 2 times 3 times 5. Let's do one more of these. What is the prime factorization of 73? Now 73 is interesting. It looks, 73, I'll get my scratch paper out for this. We could try to factor 73. So you might try 2. Well, this is clearly an odd number, so 2 isn't going to be divisible into 73. You might try 3. You would immediately see, well, 3 is divisible into 72. If you divide into 73, you have a remainder of 1. 4 isn't divisible. Well, 4 isn't a prime number, so we wouldn't even try. 5 isn't divisible into 73. It doesn't end in a 5 or 0. 7 is not divisible into 73. 7 goes into 70, so you'd have a remainder of 3. 11 isn't divisible into 73. It's divisible into 66 or 77, so not 73. So it looks, as I test more and more numbers, it doesn't look like there's any easy thing that divides into 73. So I'm willing to go with 73 itself is a prime number. So this is its prime factorization. It's just 73. So let's write that down. So the answer here, let's just write 73. And you don't want to write 1 times 73 because 1 is not a prime number. You just want to remember it only has one factor, itself. A prime number has two factors, 1 and itself, two different prime factors, 1 and itself is not 1. So we just want to write prime numbers here. 73 is a prime number. Let's check our answer. And we got it right. In this video, I want to do a bunch of example problems that show up on standardized exams, and definitely will help you with our divisibility module because it's asking you questions like this. All numbers, and this is just one of the examples, all numbers divisible by both 12 and 20 are also divisible by. And the trick here is to realize that if a number is divisible by both 12 and 20, it has to be divisible by each of these guys' prime factors. So let's take their prime factorization. The prime factorization of 12, let's see, 12 is 2 times 6. 6 isn't prime yet, so 6 is 2 times 3, so that is prime. So any number divisible by 12 needs to be divisible by 2 times 2 times 3. So its prime factorization needs to have a 2 times a 2 times a 3 in it. Any number that's divisible by 12. Now, any number that's divisible by 20 needs to be divisible by, let's take its prime factorization. 2 times 10. 10 is 2 times 5. So any number divisible by 20 needs to also be divisible by 2 times 2 times 5. Or another way of thinking about it, it needs to have 2 2's and a 5 in its prime factorization. Now, if you're divisible by both, you have to have 2 2's, a 3, and a 5. 2 2's and a 3 for 12, and then 2 2's and a 5 for 20. And you can verify this for yourself, that this is divisible by both. Obviously, if you divide it by 20, let me do it this way. Dividing it by 20 is the same thing as dividing it by 2 times 5. So you're going to have the 2's are going to cancel out, the 5's are going to cancel out. You're just going to have a 3 left over. And if you were to divide it, so it's clearly divisible by 20. And if you were to divide it by 12, if you divide it by 12, you divide it by 2 times 3. This is the same thing as 12. And so these guys would cancel out, and you just have a 5 left over. So it's clearly divisible by both. And this number right here is 60. It's 4 times 3, which is 12, times 5. It's 60. This right here is actually the least common multiple of 12 and 20. Now, this isn't the only number that's divisible by both 12 and 20. You could multiply this number right here by a whole bunch of other factors. I could call them A, B, and C. But this is kind of the smallest number that's divisible by 12 and 20. Any larger number will also be divisible by the same things as this smaller number. Now, with that said, let's answer the questions. All numbers divisible by both 12 and 20 are also divisible by, well, we don't know what these numbers are, so we can't really address it. They might just be ones, or they might not exist because the number might be 60. It might be 120. Who knows what this number is? So the only numbers that we know can be divided into this number, well, we know 2 can be. We know that 2 is a legitimate answer. 2 is obviously divisible into 2 times 2 times 3 times 5. We know that 2 times 2 is divisible into it, because we have the 2 times 2 over there. We know that 3 is divisible into it. We know that 2 times 3 is divisible into it. So that's 6. Let me write these. This is 4. This is 6. We know that 2 times 2 times 3 is divisible into it. I could go through every combination of these numbers right here. We know that 3 times 5 is divisible into it. We know that 2 times 3 times 5 is divisible into it. So in general, you can look at these prime factors, and any combination of these prime factors is divisible into any number that's divisible by both 12 and 20. So if this was a multiple choice question, and the choices were 7 and 9 and 12 and 8, you would say, well, let's see, 7 is not one of these prime factors over here. 9 is 3 times 3. So I need to have 2 3's here. I only have 1 3 here. So 9 doesn't work. 7 doesn't work. 9 doesn't work. 12 is 4 times 3. Or another way to think about it, 12 is 2 times 2 times 3. Well, there is a 2 times 2 times 3 in the prime factorization of this least common multiple of these two numbers. So this is a 12. So 12 would work. 8 is 2 times 2 times 2. You would need 3 2's in the prime factorization. We don't have 3 2's. So this doesn't this doesn't work. Let's try another example just so that we make sure that we understand this fairly well. So let's say we want to know, we ask the same question. All numbers divisible by, let me think of two interesting numbers. All numbers divisible by 12 and let's say 9, 9 and I don't know, let's make it more interesting. 9 and 24 are also divisible by. And once again, we just do the prime factorization. We essentially think about the least common multiple of 9 and 24. You take the prime factorization of 9, it's 3 times 3, and we're done. Prime factorization of 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So anything that's divisible by 9 has to have a 9 in its factorization, or if you did its prime factorization, it would have to be a 3 times 3. Anything divisible by 24 has got to have 3 2's in it, so it's got to have a 2 times a 2 times a 2. And it's got to have at least one 3 here. And we already have at least one 3 from the 9. So we have that. So this number right here is divisible by both 9 and 24. And this number right here is actually 72. This is 8 times 9, which is 72. So if the choices for this question, let's assume that it was multiple choice. Let's say the choices here were 16, 27, 16, 27, 5, 11, and 9. So 16, if you were to do its prime factorization, is 2 times 2 times 2 times 2. It's 2 to the fourth power. So you would need 4 2's here. We don't have 4 2's over here. I mean, there could be some other numbers here, but we don't know what they are. These are the only numbers that we can assume are in the prime factorization of something divisible by both 9 and 24. So we can rule out 16. We don't have 4 2's here. 27 is equal to 3 times 3 times 3. So you need 3 3's in the prime factorization. We don't have 3 3's. We only have 2 of them. So once again, cancel that out. 5, 5's a prime number. There are no 5's here. Rule that out. 11, once again, prime number. No 11's here. Rule that out. 9 is equal to 3 times 3. And actually, I just realized that this is a silly answer because obviously all numbers divisible by 9 and 24 are also divisible by 9. So obviously 9 is going to work, but I shouldn't have made that a choice because that's in the problem. But 9 would work. And what also would work is if we had if 8 was one of the choices, because 8 is equal to 2 times 2 times 2, and we have a 2 times 2 times 2 here. 4 would also work. 4 would also work. That's 2 times 2. 6 would work, since that's 2 times 3. 18 would work, because that's 2 times 3 times 3. So anything that's made up of a combination of these prime factors will be divisible into something divisible by both 9 and 24. Hopefully that doesn't confuse you too much. Let's say that today, and we'll call today day 1. Day 1 is a Monday. What I want to figure out is, what is day 300 going to be? Day 300. What day of the week will day 300 be? And I encourage you to pause this video and think about that a little bit.